If an alien civilization visited us tomorrow, the most objective way they could measure our progress would be by the total amount of power we can harness. This chart shows the Kardashev Scale, a metric that categorizes civilizations by whether they capture the energy of their planet, their star, or their entire galaxy. Right now, humanity barely registers on it. The incident solar energy hitting Earth is about 0.5 billionth of the sun's total output, and we can't even use most of that fraction. 70% of our planet is covered by water, and the remaining landmass is heavily skewed toward polar regions and harsh environments where a large-scale solar collection is highly inefficient. To understand our limits, you just have to look at the mass of the solar system. The sun contains nearly 99.9% of everything. Of the tiny fraction that is left, the vast majority of the rest is Jupiter. Earth sits in the microscopic miscellaneous category. We are a tiny dust mote trying to power a global industrial base, and we are hitting a harsh ceiling on this dust mote. Scaling up artificial intelligence requires escalating amounts of electricity. Along with that immense power draw comes waste heat, which is incredibly difficult and expensive to manage here on the ground. But in orbit, the environment works for you. You have continuous, unfiltered solar energy, and you can dump waste heat directly into the freezing vacuum of space. Putting massive server racks in orbit is the logical next step to capturing a meaningful percentage of our star's energy. But actually pulling off a space-based data center requires overcoming 3 physical hurdles that have blocked industrial expansion for decades. The first limiting factor is gravity. Lifting millions of tons of heavy silicon chips, metal racks, and solar arrays out of Earth's atmosphere has historically been too expensive and too slow to even consider. Look at the Saturn V rocket. It represented the absolute peak of expendable launch vehicles. But because you throw the hardware away into the ocean after every single flight, the cost per kilogram strictly prohibits building massive orbital infrastructure. The math only works with full and rapid reusability. By catching a booster out of the air with a massive launch tower, it can be inspected, refueled, and flown again within hours. Right now, total global launch capacity hovers around a few thousand tons per year. By operating rockets like commercial airplanes, that single design scales our launch capacity to millions of tons annually. The orbital mass barrier disappears. Once you can cheaply move the mass, the second hurdle is architectural. You have to take everything inside a climate-controlled terrestrial server farm and redesign it to operate independently in zero gravity. This diagram shows the proposed blueprint for the AI-1 satellite. Its computing core is built to handle about 150 kilowatts of peak power, making it the functional equivalent of a massive top-tier AI server rack down on Earth. To feed that compute, it relies on massive 70-meter wings covered in solar arrays, and to shed the extreme heat generated by the processors, it uses massive double-sided radiators oriented vertically away from the sun, dumping the thermal load directly into the vacuum. Instead of massive, complex antennas, each orbital rack fires straight-line laser links directly to the existing Starlink constellation. That existing network then routes the data down to Earth with latency as low as 3 milliseconds. Because this relies on solar and laser technologies already functioning in orbit today, the orbital data center has moved from a theoretical concept to an immediate production objective. But launching a few prototype satellites is very different from capturing a measurable percentage of the sun's output. To do that, you need millions of processors. You need a facility strictly dedicated to scaling AI chip production to volumes the semiconductor industry has never attempted. This is the proposed terafab. This chart shows the physical scale required to produce a terawatt of space compute. It starts with the outline of Tesla's massive Gigafactory Texas, and then requires multiplying that footprint by 10, resulting in a staggering 100 million square feet of manufacturing space. Overcoming this specific manufacturing limit is what takes this from a series of isolated satellite launches and turns it into an integrated, planetary-scale computational swarm. The deployment schedule starts quickly. The initial goal is to launch enough hardware to hit an annualized rate of 1 gigawatt of space-based compute by the end of next year. This chart shows the intended growth curve from there. The target is to scale by an order of magnitude each year, hitting 10 gigawatts in 2.5 years, 100 gigawatts in 3.5, and eventually reaching a full terawatt. But civilization will eventually demand more than a terawatt of power, and once you cross that line, launching that much raw metal and silicon out of Earth's gravity well becomes completely unviable, even with reusable rockets. To go larger, you have to move industrial logistics entirely off-planet. You have to manufacture the solar panels, radiators, and eventually the chips themselves directly on the surface of the moon, using local lunar materials. The moon has only 1/6 of Earth's gravity and 0 atmosphere. That means you don't need rockets to launch lunar-built infrastructure. You can use an electromagnetic mass driver, essentially a massive railgun, to accelerate finished satellites directly into deep space. By systematically removing the limits of Earth's gravity, dumping thermal constraints into the vacuum of space, and scaling production to planetary sizes, we are building the industrial foundation of a star-powered civilization.